Hey, what is up everybody? It is Mr. Boylan, and today, what in the heck are we gonna do? In this video, we are gonna perform stoichiometric calculations. Yes! Including determination of mass and volume relationships between reactants and products for reactions involving gases. As always, breaking it down a little bit. First thing we're going to do is use volume ratios to determine the volume of any gaseous reactant or product in a balanced chemical equation. Numero dos. 2. We are going to use the gas laws to calculate volumes, masses, or molar amounts of gaseous reactants or products. So basically, we're going to put a lot of this unit together as well as use a lot of information from previous units. Alright, so first, Gay-Lussac's law of combining volumes of gases is really going to set us up for study of the stoichiometry of gases. It simply states that at constant temperature and pressure, the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. So as we take a look at a reaction in which all of the reactants and products are gases, you need to recognize that the coefficients in the balanced chemical equation can also represent the volume ratios for those different reactants or products that are in the gas phase only. So in this example, where all reactants and products are in the gas phase, there exists a ratio where 2 equal volumes of hydrogen plus 1 equal volume of oxygen will yield 2 equal volumes of water vapor. Again, keep in mind that those coefficients give us the volume ratio. So if you had 2 larger equal volumes of hydrogen gas and 1 equal volume of oxygen gas, you would make 2 larger equal volumes of water vapor. Or similarly, if you had 2 smaller equivalent volumes of hydrogen gas, 1 equivalent smaller volume of oxygen gas, you would make 2 equivalent smaller volumes of water vapor. Boom! Gay-Lussac's law of combining volumes of gases. Gases only. Now, it's really important to keep in mind that that only applies to gases, and many times you are working with equations where not everything is a gas. So we must remember that the balanced chemical equation is always going to relate the amount in moles regardless of the state of matter. So it doesn't matter if it's a solid, liquid, or gas, coefficients will always represent moles. But with gases, it can also represent volumes. So when we're talking about stoichiometric calculations involving gases, oftentimes we're given the pressure and temperature conditions under which the volume of the gas is measured. We can then use the ideal gas law to determine the amounts in moles simply by rearranging the equation, or determine the volumes from the amounts in moles. Now, there's a really great graphic on your screen right now, and I encourage you to pause the video and take a moment to sort of study it. But this, in a nutshell, sort of works you through how you're going to solve stoichiometry calculations with gases. First, keep in mind that when you're at STP, you can just use that 1 mole equals 22.4 liters relationship. Otherwise, the general plan for what you need to do is on your screen there. Note that if you're given pressure, volume, and temperature conditions of a gas, reactant, or product, just convert it to moles using the ideal gas law. Then compare it using your balanced chemical equation to figure out the amounts of the other reactant or product. If that other reactant or product is a gas, you can use the ideal gas law again to determine either the pressure, volume, or temperature of that second gas. We're going to do some quick stoichiometry problems here, starting with problem number 1 and 2. It says propane C3H8 is a gas that is sometimes used as fuel for cooking and heating. Ooh, real life chemistry. I thought I was never going to use this. The complete combustion of propane occurs according to the following equation. Boom! Balanced chemical equation. My life is great. Question 1. What will be the volume in liters of oxygen required for the complete combustion of 0.250 liters of propane? Assume that all volume measurements are made at the same temperature and pressure. Now that's key because we can use Gay-Lussac's law of combining volumes to very quickly determine the amount of oxygen needed. Because the coefficients in the balanced chemical equation, although they will always relate the ratio of moles, with gases they will also relate the ratio of volumes when measured at the same temperature and pressure. So if we have 0.250 liters of propane and we want to know how many liters of oxygen is needed for the complete combustion of that propane, we can simply use the coefficients in the balanced chemical equation, which in this case is a 5 to 1 liter relationship. Notice that my units of liters of propane will cancel out and I'll be left with liters of oxygen gas. I don't even need my calculator on this one. 1.25 liters of oxygen gas will be needed to completely consume the 0.250 liters of propane. Again, for gaseous reactants and products, when you're measuring their volumes at the same temperature and pressure, the coefficients in the balanced chemical equation provides you a volume ratio. Question 2. What will be the volume of carbon dioxide produced in the reaction? Again, assume that all volume measurements are made at the same temperature and pressure. Again, because we're making that assumption that volume measurements are made at the same temperature and pressure, we can start with our original amount of propane, except this time compare it to carbon dioxide. The relationship between these two is a 3-to-1 relationship, so I would expect to make only 0.750 liters of carbon dioxide gas. Box in my final answer, boom, and we're done.